Hi everyone, welcome to this webinar in our MPS Now lab. My name is Francesca Estrellas and I'm an applications engineer at Monolithic Power Systems. And I'm joined by Xavier Rivas, who is also an applications engineer here in Barcelona, Spain. We are going to present the webinar on how to design a good two-layer PCB for automotive applications that can meet stringent EMI limits and have good thermals. We are joined on the phone by Jens Hedrick and Christian Cook, who are both applications engineers in Central Europe. You can contact them via this link in case you have any technical or commercial question. The agenda for today is an introduction on why we did this study of two-layer PCB versus four-layer PCB, then a brief recap on what are the differences between these two types of PCBs, and then we will introduce the MPQ4323, which is MPS' newest compact and value line back converter. We have used this device for all the comparisons, so we will give a recommended schematic for the design in two-layer PCBs, recommended layout, placement, filter design, etc. for this device to meet EMI and have good thermals. Then we will do a comparison of the same configuration with two different PCBs to see the effect that one layout can have in the thermals of your design. Then we will also compare MPS part, MPQ4323, to our competitors. We will show the difference in thermals. Then at the end, we have some EMC results from our recommended PCB. You will see that the results are very good, so we can back our claims. And we have some conclusions. So let's start with the motivation. From MPS, we have seen an increasing cost pressure in our customers to have very cheap PCBs. Most of them are trying to use two-layer PCB, where typically they would have used four-layer PCB in order to save cost. Automotive EMC limits are very hard to meet in a four-layer PCB, so they are even harder to meet in a two-layer PCB, as we will show later. Also, the ambient temperature requirements have reached higher than 100 degrees Celsius in some applications. This makes it critical that we can extract all the heat from the IC converter and dissipate it to the ambient. We want to avoid that the junction temperature of our IC reaches its absolute maximum rating. In most MPS parts, this rating is 150 degrees Celsius. Many customers reach MPS asking for a guideline on when designing two-layer PCB. So we decided to conduct an experiment by making this PCB panel with different layout implementations to check what effect each implementation has. We wanted to find out if there is any compromise needed when trying to design for EMI or trying to design for thermals. In the end, we discovered that the best PCB for thermal performance is also the best PCB for EMI. We will show it now. First of all, an introduction of what is the difference between a four-layer PCB and a two-layer PCB thermally and EMI. First of all, here we have the typical layer stack for a four-layer PCB. We have the signal layer on the top layer, where we place the components here and most of the power tracks. And then on the second layer, the internal one, we have a ground plane. We want this ground plane to be uninterrupted so that it can be a good return path for all the signals on the top layer. Also see that this distance between the signal layer and the ground plane is very small. We recommend it having 0.2 millimeters or smaller. This allows to have a very small parasitic impedance for the signals to its return. And also it is easier to contain the electromagnetic fields emitted by the copper planes and the components, and also to contain the eddy currents. Then on the third layer, also internal, we recommend routing here the signals that are very noisy, like data clock, high-speed data clocks, and any other signal that could not fit on the top layer. This signal is shielded by this ground layer here on the second layer, and the ground plane also on the bottom plane. So this layer is shielded, and the EMI that these signals can emit doesn't reach the exterior. Then on the bottom layer, we recommend again having a ground plane uninterrupted. This is so because we have this layer with quiet signals that won't couple into our chassis of the system or to the EMI setup, so we will get much better results. On the other hand, we have a two-layer PCB, which is much more simple, but also it makes the design more complicated. So on the top layer, we have the signals and the components placed here. We want to route everything as possible here on the top layer. And then on the bottom layer, we would ideally have an uninterrupted ground plane so that it acts as a good return for our signals on the top. Realistically, we are not going to have enough room on the top layer to route everything, so we will most likely have to route some signals on the bottom layer, interrupting this ground plane and making the return paths larger. Also, you can see that the distance from the top layer to the ground layer is much wider. It's actually 8 times the distance on a 4-layer PCB. So the signals will have a much larger parasitic impedance to their return. If we look at the thermals, here on the left, we have a 4-layer PCB running with the MPQ 4323 at 13.5 volts input, 5 volts output, and 3 amps of output current, and switching at 430 kilohertz. After 2 hours, we can see an increase of temperature on the case of the device of 20.4 degrees Celsius. If we compare it to the 2-layer PCB, here on the right, with the same conditions, we'll see an increase of temperature on the case of 32.1 degrees Celsius. This is a 12 degrees difference, and it is very significant because it reduces our operating range for ambient temperatures. Now I'm going to quickly present the MPQ 4323, which is MPS newest value line back converter. It is a very compact in 2 by 3 millimeters, and it is a family of pin-to-pin compatible parts that cover from 0.5 amps to 4 amps. It has a no-load current of 20 microamps, very low, and a peak efficiency of 96% at around 1 amp of output current. We have adjustable frequency, adjustable output voltage, and also many fixed output versions with these values, so that you don't need any resistor dividers. It also has frequency spectrum, among many other features. Since it is a very simple part, we have used it as a comparison for our layout investigation. In all the different PCBs, we use the same schematic, and we recommend this schematic for all the 2-layer PCB designs. Here on top, we have the input protection. We have a TVS, a reverse battery protection diode, and then we have some capacitors for filtering. These capacitors are directly connected to the battery line, so they need to be safe capacitors. And we need to use the smallest case that we can tolerate for the creep edge rules. These capacitors need to be of low value, and they are very helpful when filtering high frequencies. For larger capacitances, we have used this implementation of 92 capacitors connected in series and in 90 degrees in the layout, as you will see later. This allows us to use non-safety capacitors, which are much cheaper. And this high-value capacitance will help us filter the fundamental switching frequency of the converter and its low-frequency harmonics. Then after the diode, this diode will act as a fuse if anything happens to these capacitors. So we can start using cheaper capacitors and not bother with the safety ones. Here we have the input filter. We place a placeholder for a ferrite bit in case it was needed. As you will see later, the EMI results were so good that this was not needed. So we ended up not populating it. Then we have the input filter with a cheap semi-shielded inductor and a couple of capacitors. The input capacitance, the DC-DC converter, the bootstrap, the power inductor. We used a high-quality one, but for higher switching frequencies, you could use a very small inductor of 1 microfarad or 2.2 microhenries, sorry. And the output capacitors. Then here we have the resistor divider for the feedback and a couple of passive components for configurations. Now my colleague Xavi and I are going to show the PCB. So here on the left, we have the input connector, where we connect the cables of the harness, and we have the filtering capacitors and the protection diode and TVS. We place these filtering capacitors as close as possible to the connector. Then here we have the input filter with the inductor and a couple of capacitors. An electrolytic capacitor to smoothen out the input voltage of the converter. And then at the center of the PCB, we have the MPQ 4323. As you can see, it is a very small device, and it is smaller than most of the passive components on the application. Here on the left, we have the analog components that help us configure the switching frequency and the output voltage. On each side of the converter, we have the symmetrical input capacitors, with the bulk capacitor placed further away from the device, and the smaller capacitor placed closer so that it can absorb the high frequency noise. We have a power inductor, the output capacitors, and the bootstrap. Here it is a close-up image so that you can see it better. Input filter, analog components, input capacitors on each side of the device, the bootstrap, the power inductor, and the output capacitor. By placing these capacitors symmetrically in our package, they have a very high DIDT running through them, so they generate high magnetic fields. By placing it in a symmetrical orientation, the magnetic fields are in opposite polarization, so they cancel out. So the magnetic field emitted from these capacitors cancels the noise from these capacitors. We get a much quieter PCB this way. Now I'm going to give some layout tips when designing the DC-DC converter. We switch to the CAD view because it's easier to see the copper here and the polygons. Our first recommendation is to use a white copper polygon for V-in. Our ICs are designed in a lead frame technology, flip chip, that connects directly the silicon die with the power MOSFETs and everything directly to the PCB via lead frame, which is the patch that you solder on the board. This way, we get a very small thermal resistance from the die to the copper areas. We want to take advantage of this by connecting all the pins that are connected to the power MOSFET, so V-in, ground, and the switch node, with white connections. By connecting V-in to this copper polygon, we achieve a lot of heat dissipation, and we also get this symmetrical input that will cancel the fields on each side. Our second recommendation is that even though that the switch node is connected to the power MOSFETs, we do not want to dissipate heat from here because the trade-off with EMI is too high. We recommend keeping this node with an area as small as possible, just enough to carry the output load of 3 amps. We place here a test point and a power inductor, but we don't use more area than needed here because this node has a very high DVDT swinging between ground and V-in at a very rapid speed, so it emits a lot of electric fields. We want to keep this area as small as possible. Then the other path for heat dissipation that we have is ground. We want to connect ground with a white copper connection to our ground plane on the top layer and have many vias close to connect it also to the ground plane on the bottom layer. This way we have 2 layers for heat dissipation. We also want to have many vias close to the inductor. Because of the skin effect, the high frequency noise tends to concentrate its currents on the edge of the copper. In a typical DC-DC converter without these vias, the noise will be concentrated on the edge of the PCB, very close to our connectors, and contaminate them. To avoid this, we place many vias, and since they have a hole in the middle of them, we concentrate the high frequency currents on the hole of these vias instead on the edge of the PCB. And last, our signal pins that connect to the passive components, they are typically connected using thin copper wires. Instead, our recommendation is to use copper polygons to connect all the pins to the passive components. This way, no area is wasted. Since we are using this flip chip technology, all the signal pins also have copper pillars connecting the die to the PCB. So we have also a small thermal resistance, and we can use every square millimeter here that we can get for heat dissipation. Now, on the bottom layer, we want to route as few signals as possible. We want to route only the susceptible signals like feedback and the other signals that we could not fit on the top layer. Here we have the feedback trace, which goes from our output capacitors to our resistor divider very close to the IC. We want to route this signal far away from the noisy signals like bootstrap and switch node. In case we are expecting high noise to be injected in our PCB via electromagnetic interference or under our typical automotive tests, we can route this signal in a stitching way. So for example, we would start on the bottom layer, route for some length, then we will change to the top layer, route for a certain length, then switch again to the bottom layer, and so on and so on. This way, we would avoid having a too long signal on a single layer, so that when the noise is injected from a directional standpoint, the signal is short enough that it only picks up very high frequency noises that are not in our tests. The other signals that we routed here are the bootstrap and the power good. We route them as straight as possible and short as possible in order not to interrupt the ground plane. Now some tips when designing the input filter. First of all, as we mentioned, these small capacitors, right close at the connector, they help filtering high frequencies. The value should be between 1 nanofarad to 47 nanofarads to filter different frequencies on the FM band or higher radiated, if you have problems at higher radiated frequencies. These capacitors need to be of the smallest case possible in order to have a very small parasitic inductance. The second recommendation is to place the two capacitors with a 90 degrees orientation in order to avoid any damage in case one of them cracks due to mechanical stress or any damage on the PCB. This way, we are not short-circuiting V into ground, and we avoid fire. These capacitors help filtering the fundamental switching frequency and the low-frequency harmonics. Then for the actual input filter, we want to connect the capacitors in a symmetrical orientation, as similar as the input capacitors for the DC-DC converter. This way, any AC high-frequency noise that is running through these capacitors will emit a magnetic field that is cancelled out by the other capacitor having a magnetic field in the opposite direction. Our last recommendation is that for the input filter, here there would be the DC-DC converter. The first thing that the DC-DC converter needs to see from a connection standpoint is an inductor. This way, the high frequency noise sees a large impedance and doesn't go this way. We want to avoid having any ceramic capacitors close to the filter inductor in the DC-DC being net. These capacitors would carry very high DI/dt, and they would emit a magnetic field that it could couple to the inductor or directly to the input trace, making the input filter useless. So keep all the ceramic capacitors and the switching elements like the inductor far away from our filter. The electrolytic capacitor here down, there is no problem here because this capacitor doesn't carry high frequency noise. It has too large ESR and ESL. Now I'm going to show a comparison between the traditional MPS layout that we would recommend to our customers before doing the investigation. There are a couple of big differences here compared to the layout that we just discussed. First of all, we have a ground plane on the top layer that has a cut around the DC-DC converter area. You can see it very clearly here in this thermal image because all the heat gets concentrated here. We did this in order to avoid the high frequency currents reaching the edge of the PCB. We thought that by having this cut, the high frequency currents would be concentrated on the edge of this polygon. And this is very good for EMI, but as you can see, it is not so good for thermals. We concentrate all the heat in this area. Also, the other thing that is different is that we connect V with a trace on the bottom layer, and then it does this Y shape to create the input, the symmetrical input. Here you can see the vias for the connection of V, and there is actually a very small copper plane, copper polygon connecting V on each side. So we didn't take advantage of the capability of this signal to evacuate heat. On the other hand, we have our recommended layout that we just showed, and we see a 6 degrees improvement on the case temperature by having this very wide V copper polygon connected to it, and also an uninterrupted ground plane on the top layer. We see that the delta temperature at the IC after 4 hours of runtime on the old layout was 46.8 degrees Celsius, while on the newer layout, it is 40.7 degrees Celsius. This allows to increase the ambient temperature at which this device can operate. Then we have also done a thermal comparison between MPS part, the MPQ 4323, to our competitor's part, which is pin-to-pin compatible. We did a direct comparison by having a similar setup. So MPS part is switching at 430 kilohertz. The input voltage is 13.5 volts, and the output voltage is 5 volts with a load current of 3 amps. We achieve an efficiency of 88.9%. Our competitor's part is switching at 400 kilohertz and has the same input and output. In this case, the efficiency is 88.4%. The 0.5% difference translates into 120 milliwatts of increased power dissipation. So you can see MPS part is more than 4 degrees cooler than our competitors. We achieved this by having a better efficiency and also by having a better lead frame design. So the connections between our silicon die to the PCB are wider in the MPS lead frame, and we get a smaller thermal resistance. Now I'm going to show some EMC results from our recommended layout, because you will see that having good thermals is not a compromise with having good EMC. Here on the left, we have the conducted emissions, and we have made the test at 430 kilohertz and at 2.2 megahertz switching frequency to see the difference. With a low frequency device, you can see the fundamental switching frequency here at 430 kilohertz, attenuated by our frequency spectrum. You see the first harmonic, second harmonic, the amplitude is very small. And then what is interesting is at the high frequencies, which are usually the most complicated for automotive designs. Here we can see at the FM band, the maximum average noise for the EMI is 4 dBs. This is very far away from our CISPR25 limits for average noise at 18 dBs and the strict OEM limits at 12 dBs. We have a big margin, so this means that we can cut down on cost maybe on the inductor. We can use a cheaper inductor. We can remove a bit of the input filter. So this is a very good implementation. Then for the 2.2 megahertz switching frequency, it is a bit more complicated, usually in EMI. We have the fundamental switching frequency here, greatly attenuated by our input filter, so we could make it smaller. We have the harmonics here. And then at the high frequencies, in the FM band, and so we have higher noise of 9 dBs in this case. It is a big increase compared to the low switching frequency part, but still we are far away from the limits, from the CISPR25 limits and OEM limits. Then on the right, we have the radiated emissions for monopole test. And you can see that here, spectrum is saving us in the third harmonic noise. If we didn't have spectrum here, the noise spike would be a bit higher and potentially reaching the limit. But since we have a spectrum, we contain all the noise here. Then these are the tests for the radiated emissions test at 30 megahertz, between 30 megahertz to 200 megahertz, with the low switching frequency part and the high switching frequency part, with horizontal and vertical polarity. Here you can see that there is not much noise involved in these bands, and there is not a big difference between the two switching frequencies. Then for the higher frequencies, here we have the test between 200 megahertz to 1 gigahertz. As you can see, there is more noise here to be seen, especially on the high frequency operating part. The low frequency operating part has a lot of margin at all ranges, so it is a very good result. And for the 2.2 megahertz part, we see some noise spikes, but still we are far away from the limits, and we have sufficient margin everywhere. The noise that we see here is potentially created by our test setup. We are using a load resistor connected to our PCB. But in a real application where you have the load on the same PCB as the DC-DC converter, the noise seen at this area is much lower typically. As you can see, we have a lot of margin everywhere, so a 2-layer design can pass automotive EMI without any issue. The conclusions from this presentation are that the MPQ4333 allows a cost-effective 2-layer PCB design to perform well in harsh environments like automotive. The IC can achieve close to full output operation in ambient temperatures that reach 100 degrees Celsius when operating at 400 kilohertz, and approximately 80 degrees Celsius when operating at 2.2 megahertz. We have also seen that the MPQ4333 is thermally superior to our direct competitor's part due to a larger bump connection in the lead frame and higher efficiency. And last, we have seen that a low-cost design can pass EMI tests with CISPR25 and OEM limits with sufficient margin. Typically, our customer boards might not have this perfect square shape with a lot of margin on the edges. They have mechanically constrained ports, smaller. The connector are not placed on ideal place. So having all this margin really helps. If you follow our tips on design, I'm sure that many PCBs can pass EMI in a 2 layers design. Also, since the MPQ for P333 is so small, it gives a lot of flexibility to place it on the ideal place on your PCB. Thank you for listening, and now we will do a QA session, so feel free to submit them in the QA panel. Thank you.
So if somebody has a question, you can ask through the QA panel or raise your hand, and we'll allow you to talk directly the question. So some of the attendees is asking if the datasheet is available for the 4323, and if there is any evaluation board available.
I might chime into it, and also it's an early part. Parts are available, and also the datasheet is available on request, but it's not on the web yet.
Okay, thank you, Christian. There is another question regarding if this report will be available online. Certainly the webinar will be available online. The report from CES, maybe you can update.
I might add to that that the webinar will definitely be available on the on our Monolithic Power website, as the other webinars are. It may take maybe a few days until it's uploaded, but if you click there under support, now you will find the webinars, and in a few days you also will find this webinar.
Yeah, and if you're interested in the material or the data sheet, please contact your local MPS sales force or our sales force, your sales contact, and we will provide you the data sheet and the test report.
So there is another question regarding if it's better to have a bootstrap trap short on the top layer or in the inner layer. I imagine for a 4 PCB, for example.
So I will answer. If it's in a 4-layer PCB, then we would recommend to route the bootstrap on the internal layer 3. And for with this device, because the pinout of the device doesn't allow to directly connect the bootstrap between the switch node and the pin, so it needs to be on a different layer. In a 4-layer PCB, we would recommend the internal layer. This way, we shield these trays. And in a 2-layer PCB, we have to resort to the bottom layer.
So we have another question. It is better to have a hot path on the inductor cut out in GND layer or have it solid?
Yeah, I might chime in. I mean, it's Jens' favorite question. Typically, you try to make the switch node and also the switch node part under the inductor as small as possible. So keep the rest area under the inductor either V out, which is also not noisy because it's heavily decoupled by the output capacitors, or if you have a larger inductor, you could make a ground lane under it. Now, but the general rule is even under the inductor, keep the switching part as small as possible in the layout. No? So that's a general recommendation. If the other part is ground with a cut through, or if it's V out, no, probably doesn't make much difference, but it should be quiet. No? So.
Yeah, especially in a two-layer PCB, if we have a cutout under the inductor, then all the magnetic fields and electric fields that it emits can go through the PCB very easily. So if we have a copper under the inductor, we avoid having these electrical fields spread everywhere, especially on the bottom side of the PCB. By having ground plane, we might sacrifice a bit of inductance, and we have some milliwatts of power loss, but we avoid having very strong electrical fields on the bottom layer of the PCB.
So the same customer, it's asking, it's EMC lower with the full GND under the hot path of the inductor. I imagine it's referring to the switch node also. And what do you think?
Yeah, the thing is, you need definitely under the switch node and the magnetic hot loop, now covering also the incapacitor, a solid plane under it. If on a two-layer PCB, the only chance is to have it on the other side, but it needs to be solid with as least cuts as possible, because you do not want to have a magnetic and electric field sticking out on the bottom side of the PCB. So you need a solid plane, and as close as a solid plane to the hot loop is as better. But even on this part with a two-layer PCB, it's sufficient. But you can't make any really large cuts or something under it. So in general, if you can look through a PCB in the area of the hot loop, you have a problem. So you have to make it solid.
There is another attendee who is asking, what is the microflights values of the electrolytic you propose here? Some EMs do not recommend use electrolytic capacitors parts.
I mean, in general, it doesn't matter if you have electrolytic or something else. The real trick here is that every power supply is for its input a negative impedance. So there's a tendency of potential oscillation, which means you need at the input some capacity which has some losses, some ESR. If you make it a polymer or you make a larger ceramic with some series resistance or so, doesn't matter now. Electrolytic was here just chosen because it's probably the cheapest way to get some capacitive with some damping, read some ESR, so some losses.
So I think you want to add something, Jens? I saw in
the value of the cap is 47 microfarad.
Okay. Okay, you can also ask if you want to raise your hand to talk or discuss something. It could be also done. If not, we give some time more for next QAs. Okay, it looks there is not more QAs. Thank you to all the panelists, and thank you to all the attendees on this webinar. The next ones will be in the afternoon in US time for motor and wireless power. and tomorrow we will keep doing new webinars from the MPS Now Lab in Barcelona. Thank you very much, and have a good day.